Welcome to this presentation of our rocket design activity project. Here we will go over the main points in the design process. Our two main objectives in this project are to ensure the maximum possible flight time of the rocket and to certify the payload it carries and egg remains intact throughout. The first fundamental concept we looked at was impulse. Essentially, impulse refers to a constant force applied over a certain amount of time. In our case, constant force is represented by the thrust of our rocket and impulse by its change in momentum. To find total impulse, we can sum the impulse values over a given time period or integrate the force with respect to time, with the lower and upper bounds defining the time period. Next, we must ensure our rocket is stable in flight by taking into account its center of pressure and center of gravity. The former is the point where all aerodynamic forces on the rocket are centered, while the latter is the point where the weight of the device is considered to act. For optimal stability, the center of gravity should be above the center of pressure, to the extent where the rocket's stability margin is between 1 and 2. This value is found by taking the distance between the center of gravity and center of pressure, then dividing that value by the rocket's body diameter. Let's see how to find the optimal water volume fraction. Figure 2 shows a parabolic relationship between flight time and water volume fraction. Figure 3 shows the change in thrust and water volume fraction over time for the rocket boost phase. Water is much denser than air, so when forced out the nozzle, it generates much greater total impulse. However, an increase in water volume fraction means an increase in mass, thus weight, which acts against thrust during the boost phase. Thrust must exceed the impact of water mass on the rocket for longer flight times. The fins of a rocket play a major role in its stability. Fin position shifts the centers of gravity and pressure. For a rocket, our group settled on using 3 fins, offering sufficient stability and lower drag. In Unity, the height where the fins were placed on the rocket's body was varied and tested. With this, it was found 0.16 meters was the optimal fin position. For the fin shape, we chose a simple swept clipped delta design, which retains the aerodynamic advantages of a traditional fin, such as in the simulations, while it's providing good aerodynamics. Another key aspect of the project was the parachute system. Setting the water fraction at calculated optimal 0.4, theoretical values for flight times with where the parachute diameter were found. The figure 1 graph shows the results. The relationship was found linear. Flight time increases as the diameter of the parachute increases. This conclusion was also reflected in Unity simulations. However, what wasn't theoretically reflected were practical packing constraints. Our group actually determined that a 0.8 diameter parachute was the largest we could go with this in mind. Next, our group made use of SolidWorks to make a model of our rocket. The body is primarily a 2-liter carbonated bottle, with the cap area the placeholder for a smaller fitted rocket's nozzle. The section above and nose cone are formed from pieces of a second bottle. Below the nose, cone section is our egg, which is to be padded in place in its compartment. In conclusion, after having taken in consideration factors such as stability and flight time, and following a series of simulations and tests, our group is satisfied with the direction the project is headed. There will likely be challenges in transferring our theoretical and simulated information into something tangible. Nevertheless, our progress reflects individual and cumulative efforts within our group, without which this wouldn't be possible.